Corey, go!
Maybe like Ernie has a difference of 1 between his set and the difference of Bert's are.
I thought some of you might have said that, so I made a number line for their test grades. Hopefully, maybe this will help us. I'm going to kill the light to see if this helps us, actually. There, that might be a little bit better.
Go ahead and name it back.
So the reason I did this, really, was to give you another visual, because when they're this close to, when you have the numbers just laying next to each other like that, you might kind of lose just how spread out the numbers are. Now you can see it. See, here's your 81. Let's drop the 81 in here. That's the 80, 81. Here's your average. And that is the average for both of them, isn't it? So that, if plate of cookies, that's where your hand has to be, right? That's where your hand has to be to balance both the Ernie heads and or the Bert heads. Right? And or the Bert heads, yes? Fair enough? Good. So Corey's got an idea, which I love, by the way. The distance between the data points. So what's the distance here?
7.
7? How about here? It'd be about 12 or 13 or something like that.
13.
How about here?
12.
About 12 or 13. How about here?
6.
That's 6. What should we do with those numbers, Corey?
Average them.
Average them! Love it! Average those. 7, 13, 12, 6. Let's see, if I gave some of the 12 to the 6, some of the 13 to the 7, 20, 18, 38, divided by 4, 9-ish, somewhere in there. It's about 9.
It is 9.
It is 9. Oh, okay. Well, that's nice. Looks like I can do math. 9! How about Ernie's? Oh, go ahead, Randall. 9.2. I got that. I got that. How about Ernie's? Oh, a lot less. Good answer.
There you go. 20.
1 divided by 4 divided by 4 is 1. So we've divided, I want to call it the measure C. For Corey's measure of variation, Bert's C value is 9, Ernie's C value is 1. Now, I've never seen it before. You just invented it right now, my friend. I love it very much. Never seen it used. Can anybody see, no pun intended, C. Can anybody hazard a guess as to why you wouldn't use it?
Because if it's too much
Yes.
spread out or too...
I like to think of, wait a minute,
There's 2 of them in
There
this
are.
class.
there are. My default's going to
And
be
it's
wrong. I know my
not
default's
like
wrong. I know it's
that.
not. I know it's not. It's 5 letters. It's 6 letters. I'm off. What is it?
Alicia.
Alicia. I was going to guess Emily, so I thought it was 5 letters. Alicia. Where's my other Alicia? Okay. God bless us. And you talk all the time. I should know your names by now. Alicia. As she said, what I often do is I go to the extremes. I say to myself, suppose this was Bert's lowest possible value, but suppose these other grades he got were all perfect hundreds. This measure, I think, unfortunately, would penalize him for that low grade. It puts too much weight on the extremes. He doesn't seem to have many extremes right now because he's all over the board. It's like buckshot. But for the extremes case, he'd be penalized unfairly. Does that make sense, Corey? I think it's freaking awesome. And actually, your idea of looking at distance is spot on. It's what we do statistically. But that's a penalty, unfortunately, for the extreme outlier. Thank you, though. It's great. I would say use it in research papers and see C equals this, and let some publisher argue about whether you should use it or not. John, go ahead.
Well, I was just going to say, I might be wrong, but I think it's 14, not 13.
Oh, that's okay. It's okay. Whatever it is, we can't use it because nobody else uses it. So we can't have that. I mean, we can make up our own measure, totally fine. Except that particular one isn't commonly used, although it's pretty slick. Because I love the fact that he went between data points. Also, one might argue, why not additionally look at the distance between non-successive data points? Right? You can argue that too. And there's no argument for or against it. It's just what you would choose to do. So I love Corey's measure. It's just one that isn't used very commonly.
What if you trimmed first?
What if you trimmed? Like topped off the 100 and the 61?
Right, and then did that.
So, a caution against trimming measures of variation. It's great for averaging. But if you trim measures of variation, you can have very destructive results on the variation itself. That's a very vague statement. I apologize for the vagueness of it. But for example, if I'm just thinking of your exam. I'm thinking about my chicken flock right now. When I analyzed how many birds we had to buy to make sure we had a certain number of egg-laying chickens within certain reason, I can't trim off the outliers, which would have been all the rooster possibilities, because that would have made it look too close to 100% that I was going to get all girls. So I want to leave the I don't want to trim for this measure of variance, because the variance is unfortunately, just like Bert gets penalized for his very extreme values, you get an incomplete picture of what's going on. But I don't want to get too far away from what Corey was talking about, because what you're talking about is what is actually used. Your gut was right in the right place. I want to put the average back up there. Please!
Not Linda.
Not Linda. Not Alicia.
Or Emily. Probably.
Or Emily.
Lily.
Lily!
I took the difference between the highest score and the average, and the lowest score and the average. And
I put the average in the wrong place too, sorry. Average is actually here. So you did high minus middle, low minus middle. And what'd you do with those?
I did high minus low, and then I did high minus middle.
Oh, you did high minus low and then high minus middle. Believe it or not, that's kind of a bastardized version of what's called a mid-range.
Yeah.
So the high and the low, if you focus on the high and the low, so what would Bert's be? Bert's would be 100 minus 61, which is 39.
Yep.
Ernie's would be 83 minus 79, which is 4. Now, crazily enough, perhaps, Corey's measure of variation and Lily's measure of variation are very similar. Bert is 10 times Ernie's. Think about that. The range from high to low of Bert is about 40. Close, it's 39, but it's about 40. And Ernie's is 4. 40 is 10 times 4. Corey's measure of distance from successive data points is 4 times as big for Bert as it was for Ernie. It's very interesting that you guys have independently developed 2 measures of spread, and they come up with the same exact kind of gut. Bert's 10 times less consistent than Ernie. That's kind of fun, actually. Let's go with your halfway point too, Lily. So you said 100 down to 80, that's 20. 83 down to 81, that's 2, also. Now some of that is because the data is shaped a certain way, honestly. The only reason the range does exist. The range does exist in various places. I don't particularly like the range I don't say I just don't like it. It ignores too much. It ignores all the other data points. And there's only 2 other ones in each of these data sets, but it does ignore those guys. So I go back to the counterexample I used with Corey, which is suppose, for example, Ernie, or Bert, let's use Bert because it's more extreme, had all of his scores 61 down here, and then he had 100. That's, in my opinion, a different level of consistency than what he has right here. Go ahead.
But does it ignore it because you're using the average number?
I think we have to use the average.
You're accounting for those other numbers by using the average.
Oh, so you're saying the average itself. Okay. But I've lost how far apart they are from the average, haven't I? I love what you guys are saying. I say we put Lily and Corey's idea together, and I don't want to lose the average. That's why I keep drawing him back in. I want to talk about him. Corey, what's on your mind?
That there was 2.5 Ernie's on each side of the average, and then 3 Berts on each side of the average.
That's actually a little bit of skew. Good, go with that. How are we going to quantify that? No, 2.5 and 3, I guess.
Yeah.
Was that 16% or a third more or something? A sixth more. A sixth more Berts? I don't know how we quantify. How would we say that? 16% more variability for Bert? Maybe. Let's get far from your 10. I like your 10 times. This 10 times thing keeps showing up. That's so fun. So I like that though. The idea that if you cut the 81, you get half an Ernie head, not to be morbid, you get half an Ernie head here and half an Ernie head here, but you actually miss the Bert head. And honestly, Ernie's numbers are so perfect, Bert's heads are a little bit more realistic in that you probably won't have anything directly at average. 2.5 children per family in 1990. You don't have 2.5 kids in your family. You've got a number that averages to 2.5 when applied across. So I'm thinking, we got to get Lily and Corey's idea together. We got to not lose Corey's distance from point to point. But the thing about it is, Corey's method ignored the average, the first method. Lily's idea ignored the middle data points. Can we put them together and have a common resolution that doesn't do either ignoring thing? Can you see how we could do that?
So you get the distance between the average and each.
How about we take Corey's distances, Lily's center, and look at the distance between the data points and the average. So now, let's look at this. I want to use 2 different colors. We'll do Ernie's first, I think. Yeah, we'll do Ernie's first. So this point right here, that's 79, correct? How far is that from average?
2.
That's 2. 2 down, but just 2, a distance of 2 from average. How about the 80 itself?
1.
That's 1. How about the 81 itself?
0.
That's 0. It's at average. Exactly at, which doesn't usually happen. Doesn't usually happen. How about, how about 1? How about 2? So we got a 2, we got a 1, we got a 0, we got a 1, we got a 2. You can average those numbers right there. You see how we've used Corey's idea? Which I love, thank you. I mean, I bastardized it a little bit. But I've got Corey's idea fused with Lily's idea. If you average those, what do you get? What's that, 6 divided by 5? 1.2. 1.2 what?
On average over time.
No.
This is, unfortunately, this is one of the rare places where that won't be the right answer. The on average part's great, but there's no time to talk about because we're only talking about Ernie's 5 test grades. I've trained you guys too well at 105. On average over time, well, sometimes. Now this is Ernie's 5 test grades. What did you just add up? What do the numbers stand for? The test score, the distance is from average, right?
Yeah.
So you have 6 total points of distance away from average. Over how many tests? 5 total tests. So when you divide 6 total dispersion points by 5, you ended up with 1.2 points variation per test. And if you want to feel better about your statement, put 2 more words on it.
On average.
On average. 2 more words, not 4.
Fine.
On average, right? Because if you think about it, not
Fine.
1, that's a very low chair. Not any one of the tests, you can see my head in the camera, hi. No, in none of the tests did he actually deviate 1.2 points, right?
Right.
He deviated 2 on 2 of them, he deviated 1 on 2 of them, and he deviated 0 on 1 of them. But on average, he deviated 1.2. If you spread the total deviation evenly, remember even spread, the mean, even spread, the balanced spread, if you spread that deviation evenly, it ends up being 1.2 points per exam of deviation. Ask me questions about that. I got a great question you can ask me. Why doesn't anybody use that? Ask me that question.
Why doesn't anybody use
Okay, it's a great question. Nobody uses this measure. It's called the average deviation. It's my personal favorite, because I think you guys actually buy it right now, don't you? You're all like, yeah, you know, I dig that. That makes a lot of sense. It makes a lot of sense to me too. That's why I like starting with it. That's why, Corey, I was so excited when you did this, the distances from data points, because you actually had the right idea right there, and then Lily brings in the average, which ties it to home. Why don't we use the median instead of the average? You can. Nobody says you can't. It's just that nobody does. So it kind of goes back to Corey's idea of, you know, why don't we use yours? Because nobody's ever brought it up before. I mean, you're the first person to ever actually suggest that particular one. I'm not saying it's bad. I'm saying nobody uses it. Much like, you know, we basically have a two-party political system in this country. There are better systems, but we don't use them. We use that one. We don't have a two-party system. We essentially have a two-party system. Okay? Well, there are other parties, but they don't count for anything in the grand scheme of things. So the idea is, if we don't use that, which seems so perfectly logical, what does get used? What does get used? Well, the idea, please, and tell me your real name so I can stop calling you Linda.
Kale.
Kale, go.
Oh, I'm just thinking out loud.
Standard deviation is indeed what the name of, who's heard this besides Kale? About a third of you, about a third, maybe a quarter to a third of you. That is the measure that is used. There's a very good mathematical reason why it's used. I don't want to bore you with that. But it's the one that you hear about in research journals, which I'm assuming most of you guys have seen in research journals. Good. It's the beginning of standard error and sum of squared deviations. So what I want to do is I want to show you how to crunch standard deviation today. But I don't want you to ever forget what you just said about average deviation, because your interpretation of average deviation is the same interpretation of standard deviation. So remember how we get this was 1.2 points? What was it? 1.2 points.
Away from on.
The average. The average. You can use the word standard average wherever you want, but what does the 1.2 stand for?
Variation.
Variation per test on average, right? It's variation per test from average on average. It's kind of weird because you have to use the word average twice, because you're measuring deviation from the average, and then you're averaging that deviation. Did everybody see why you have there's just two averages at work here? There's the average that we're measuring off of, and then we're averaging those results. So there are two averages being done. So what you're looking at when you're looking at deviation is you're looking at the average distance of data points from the average of the data set. And that is what I'm going to put under measures of consistency right now. Because if you can understand that, walking out of this room today, you're in great shape for the rest of this course. That is the big idea. I'm going to erase this, not that it's not important, because it's still true. It's still true. You would think that the data is more spread out. Spread out means the distances are greater between the average and the data points, so therefore this is still going to be true. Hopefully you believe that. Imagine a buckshot. Take a buckshot taken at 10 yards versus 50 yards. It's going to have more time to spread out. You're going to have a tighter cluster closer. So you're going to be over here with a tighter cluster. But the big idea, and this is what I just want you to kind of let this ferment in your mind. We're about to get lost in some, not hard mathematics, but a little bit tedious. Teeny bit tedious. The big idea, I don't want to lose the big idea. The big idea is, it's going to measure the average distance of all the data points from, and I'm going to go ahead and put X bar in there, from the average of the data points. That is what the standard deviation at its heart is measuring. That you have to use the word average in there twice. Because the first thing you have to do is put the average on there and figure out how far apart the data points are from that average. Then you're going to have a set of numbers. Then you want to average those data points. Say that again. Well, let's do Ernie with the standard deviation that Cale brought up, because we haven't actually done the calculation of standard deviation yet. We've done the average deviation, which is so intuitive. I wish we used it more. But we don't. There's actually a command in Excel called avdev, A-V-E-D-E-V, that calculates it for you. I've got some nods, and you guys have seen it before. Yeah, it's a beautiful one. But nobody uses it in research journals. So you guys in research fields, HDFS, natural resources, psych, soc, early childhood, you're not going to see that guy in the research journals. It's okay. We're going to see standard deviation, in particular sample standard deviation. That's what I want to spend today doing, is actually calculating that sample standard deviation. So I'm going to mute the screen for a second. We'll start this before break. We'll see how far we get. I'm going to start. We'll do Ernie first.